All right, back in section 4.2 from last time, we had begun looking at prime factorization, and we had encountered this one sort of odd example, part B, when we left off, right? Where it was sort of like partially factored, and we just finished factoring it instead of multiplying everything out and redoing the whole process, because that's really not helpful. We would like to actually make it simpler on ourselves. We're going to have the same kind of thing going on part C, where it looks like it's a little bit already factored. But what's different about C than happened on B? There's an addition in there. So something else is going to have to happen here, right? Because there wasn't an addition in the step before, or in the problem before. So when we're taking a look at problem C, what we're going to be doing for factoring in this is we're going to be actually looking into each piece of this, each of the addition pieces separately, each of the add-ins separately, and we're looking for what they have in common. So what do they have in common? They have a 2, a 3, and a 7. Yes, they do. And so I'm actually going to write that 2 and the 3 and the 7 out here in front. Notice I've given them a little bit of space after each one of them. You should too. How many 2's do they have in common?
6.
They have 2 2's in common. You see, the first one has only 2 2's in it. The second one has 4 2's in it. So the number of 2's that they have in common is 2 2's. Is everybody with me on that? If it helps, what's that?
Are we not dealing with the exponents?
We are, but this first exponent just has 2 2's. Oh, we're not done with it yet. I'm just looking at what they have in common right now. So if it helps you to do this too, I'm going to draw this out for at least the first one. You could actually write out how many they have of these things. At some point here, though, you're going to stop because I don't think you want to write 7 out 55 times. Okay, so this is the first one, and then we have that 7 to the 55 here going on. So right here, there's only 2 2's in this one, and there's 4 2's over here. Okay, we're going to fix the fact that that's not all of them in a minute. We're just looking for right now what they have in common. How many 3's do they have in common? There are 4 3's in common, and how many 7's do they have in common? 55. Okay, now I've factored those out in front. Okay, I've pulled out what they have in common. What I have left to do is to write down what they don't have in common. What's left over. So in the first one, I took out all the 2's, didn't I? They're already all out of there. Do I have any 3's left over? 1 3. Do I have any 7's left over? No. So that's it. That's all that's left out of what I've pulled out. How about the second piece? Do I have any 2's left over? 2 2's. So either write that out as 2 times 2, or if you want it as 2 squared, that's fine. Do I have any 3's left out or left over? No? How about the 7's? No, they're all taken care of, right? So what I have left then is to take what's in this parentheses and simplify it. So what is 3 plus 2 times 2? It's a 7, isn't it? So right now this is 2 squared times 3 to the 4th times 7 to the 55 times another 7. Can I simplify that? Careful. Yes. How can I simplify that?
It would be 2, 7, 55.
Say again.
Like a 2 in front of the 7.
Not quite.
7.
But we do have the 7 there. 7 to the 56. So remember what 7 to the 55 means. It means there's 55 7s. So if I were to write them all out, I'd write out 55 of them. And now I have one more of them, so I have 56 of them. So the 2 squared stays the same. The 3 to the 4th stays the same. But now I have 56 7s. And those are all my pieces. Yes, Nerly?
If that number would have been like 8 or something, would you just have left it and that would have been great?
Yes and no. If the number had been like 11, I would have left it. If the number had been 8, why wouldn't I have left it?
Because you could factor it.
Because I can factor the 8, and then I would have to do that. I'd factor the 8 down into 2 cubed, and then I would combine that 2 cubed with the 2 squared I already had. Yeah. So if you can simplify it, you will. If it is something that you can't simplify, if it were a prime number or simply a number that you didn't already have listed or something like this, then you could leave it. Yeah. Does that make sense? Okay. What's next? Oh, fundamental theorem of arithmetic. Whenever you see the phrase fundamental, it means it's important, right? You've probably seen them before in mathematics. This one says, and I've actually already hit on this last class period, each composite number can be written as a product of primes in one and only one way, except that you could change the order around. We talked about that last time, right? It's really important because that means that when you factor in a factor tree and I factor with that division sort of method, we're going to get the same answer. It doesn't matter. We're going to get the same answer. If we put them in chronological order, like numerical order, increasing order, they'll be identically the same. But if I don't, I still have the same numbers. They're just in a different order. Okay, so it's a fundamental theorem of arithmetic. The next one says that if D is a divisor of n, then n divided by D is also a divisor of n. So let me give you an example of what that's talking about. So let's say we've got 3. So if 3 is a divisor of 8, not 8, 24 is what I wanted, 24. Is 3 a divisor of 24? Yeah, it divides it, right? Then what this theorem is telling me is that if I take that 24 and I divide it by 3, what will I get? 8. And I know I get a whole number 8 because that's what it means for 3 to be a divisor of 24. So 8 is also a divisor of 24. Okay, so once you get one divisor, in other words, you get 2. Right? They always occur in pairs. If you find a divisor of a number, you find 2 divisors at the same time. So if I asked you to find me a divisor of the number 12, what's a divisor of 12? 6. So if 6 is a divisor of 12, then 2 is as well, because 6 times 2 is 12. And this is all this theorem says, is that they occur, these factors or these divisors occur in pairs. All right, the next one, theorem 415, says if n is a composite number, then n has a prime factor p such that p squared is less than or equal to n. And I know it doesn't look like it, but this is actually the answer to Marilee's question last time that says, how far do we have to keep trying to divide something? Do you remember that question you had? And I said, I promise it's later in the lesson. Bear with me. This is actually the answer to the question. So let me show you how you actually find that answer. So let's pick a large number. Can you pick me a large number? Let's say a 4-digit number.
8,211.
Okay, 8,211. And you know it's not even, so now you're going to actually be forced to have to decide, is this prime? How far do I have to go trying to divide to see? Well, how far you have to go is exactly whatever the square root of 8211 is. That's why you're seeing that p squared right there. P squared is less than or equal to n. I could also say p is less than or equal to n, the square root of n. So if somebody tell me, what is the square root of 8211? I know it's probably going to look ugly because I don't think you picked a perfect. 90.6, okay? So the biggest number that you would need to check for divisibility would be the number 89. Well, technically 90, but we know it's not even. So 90 is the biggest number that you would have to go to. Now, it seems like a lot, but you have to remember you started with a 4-digit number. So if you only have to go up to 90 and you don't have to go up to 8,000, that's actually a big thing. I mean, you really don't have to go up very far. So that's actually the answer to how far do you have to go if you're trying to check for something. Now, if you already found something before you get to 90, then that simplifies things too. But if you're not finding any divisor, the furthest you would ever have to go in this one would be 90. Okay? All right, the next one, 416, says if n is a whole number greater than 1, and it's not divisible by any of these prime numbers, then it's prime. Well, yeah, right? I mean, if it's not divisible by prime numbers, it's prime. And this is actually just sort of a corollary. It's just one step further of what we were just saying in Theorem 415, right? I'm testing these, and I keep testing, and I keep testing, and if I don't have one that ever works, then it's not composite. It's going to be a prime number. Okay? All right. We're going to do an example of this one next. It's going to be smaller than 8211. It's only a 3-digit number. So it says, what is the greatest prime number you must consider to test to see whether or not 963 is prime? You're probably looking at that no already whether the answer is prime or not, but that's not the question. What's the biggest number you would have to test? So what do? You take a square root. So somebody tell me, what is the square root of 963? Oh, and I'll put an approximation here. 31 point what?
032.
Okay, sure, that's plenty. 31.032, so what is the biggest number that you would need to test? 31. And this is the greatest prime number, so we actually want to make sure that we're talking about a prime number too. And 31's prime, right? Yes, it is. Good. All right, so we can stop testing at 31. All right, part 3, or example 3 says, show that if 1 were considered a prime number, then every number would have more than one prime factorization. So let's just make a number up. In fact, we're just going to use 12 because we've dealt with it before and it's small enough to talk about. And let's do our factor tree for 12. So what is the factor tree is going to look like for 12? You have a couple options, so somebody give me one. 2 and 6, all right. And then the 2 is prime, so we stop there, but the 6 is not. So 6 is 2 and 3. So if we can use only prime numbers the way we've defined them, then 12 is 2 times 2 times 3, or we could write that as 2 squared times 3, right? Here's the problem. If 1 were a prime number, you could also have prime factorization that said this is 1 times 2 squared times 3. And these would be 2 different factorizations. But it's worse than that, because you could also have 1 squared times 2 squared times 3. And you could also have 1 cubed times 2 squared times 3. And this process could continue indefinitely, right? So when we're talking about prime factorization, there is a very good reason we do not want the number 1 to be considered prime. Because the fundamental theorem of algebra, or fundamental theorem of arithmetic that we just did before, said we should have a unique representation. And if 1 were considered a prime number, we would not have that unique representation, would we? So that would be an inherent problem. Yeah.
Sorry, because you would have to keep going like 1 times 2.
Well, so I know that you missed the part, because you weren't here last time, Nicole, right? When we talked last time, we defined what a prime number was, and one of the things we said about prime numbers is that they have 2 distinct factors, like 3. 3 has 3 and 1, 2 distinct factors. And the problem with the number 1 is the number 1 only has 1 factor. So we've defined the number to being prime so that it has those 2 factors, and one of the reasons we want that definition to be what it is for this fact. We want the prime factorization to be unique. And if 1 were a prime number, it wouldn't be. Because all of these that I've written down, plus plenty more, would be legitimate prime factorizations, and they'd all be different. That's not good. We want it to be unique. Are you guys doing okay over there?
Just under all my cupcake.
Okay. Good. I definitely should have brought napkins, I guess, huh? All right, so does that answer your question, Nicole? All right. So this is just showing you why that fact that 1 is not prime really is a necessary feature. We really need 1 to not be prime, because if 1 weren't prime, you would not have one and only one way to show this prime factorization when you're done, and that's a problem. So, all right, let's take another one. Mr. Arbor wants to plant apple trees in a rectangular array. You guys have done rectangular arrays, haven't you? That was the last section we talked about. So it says, if he has 36 saplings, find all possible numbers of rows if each row is to have the same number of trees. Okay, so imagine your cupcake tins. Imagine your containers of pop or something like that, or toilet paper rolls, right? Imagine that. So we've got that in a field where they've planted trees. So tell me one option. What is one option he could have for his 36 saplings if he did them in the same length? We've got rows and columns, and 6 and 6. That would work, right? So he could have 6 rows of 6 trees. What else could he have? Good. He could have 3 rows of 12 trees. What else could he have? 4 rows of 9 trees. What else? 2 rows of 18 trees. He could have 1 row of 36 trees. He certainly could. There are 4 more options.
Can't you do them all like reverse?
Yes, you can. Very good, Hannah. We can reverse every single one, except the first one. I mean, right, 6 rows of 6 trees is the same if I reverse it. So I can't reverse that one. But I can take all 4 of these and I could reverse them. So I could say, what? 12 rows of 3 trees. What's next? 9 rows. Of 4 trees. Yeah, but the reason is because the question actually asked, find all possible numbers of rows. So that's why we're doing it. Yeah. What else do we have? 18 rows of 2 trees. There's 1 left, right? 36 rows of 1 tree, which sounds odd, but that's okay. So these are my options. These are all of my different row options. And what you actually did when you found that is you found what? You found all the factors of 36. That's how you did the problem. You used factorization to do that. You weren't thinking it when you did it, at least not exactly, right? But that's what you were doing. You were factoring the 36 into every possible number that divides it. Okay? All right, last question in this section. Bob says that to check whether a number is prime, he just uses the divisibility rules he knows for 2, 3, 4, 5, 6, 8, 10. He says that if the number is not divisible by these numbers, then it's not prime. How do you respond? So first question is what he did okay? Will it always work? Not going to always work. So sometimes this will be sufficient, right? Sometimes it'll work, but it's not going to always work. So why not?
Don't you have to go up until like the square root of the number?
Yes. At least we might have to go up that far. How can you show him that this will not always work? Because I think that's a really good thing to do when your kids are talking to you about did something always work, is to show them, if it's not going to always work, a case where it doesn't. Wouldn't that make sense? So can you give me an example of when this will not always work?
Like if you have 49, it's divisible by 7.
That's the first one I thought of too, Marilyn. So this will not always work, and then let's take an example. For example, 49 is not divisible. Hang on, it'll show up. It'll all in one fell swoop and it'll look fun. I promise. Okay, so 49 is not divisible by these numbers, right? But what is 49? 7 squared, or 7 times 7. So 49 is 7 times 7. Thus 49 is not prime. And could we pick something besides 49 here? Is there something magical or special about 49? Not really. I mean, we used 49 because it included 7, and 7 wasn't one of his numbers in his little list. What other number could we include besides things that are divisible by 7? 11 or 13. What did you say? 81. 81. Well, 81 is divisible by 9 and 3, so 81 wouldn't work. You could not use number 11, but use a number that has a factor of 11. For example, like let's say you did 77, right? 7 times 11. Or if you did 11 squared, like we did the 7 squared, you could do 121. So you're going to exclude a lot of things, but it doesn't just exclude powers. So like 77 would be a good example that's not prime because it's divisible by 7 and 11, but 7 and 11 aren't on this list. So what he's included is a good place to start. And that's a good place to start because you guys have divisibility rules for that, right? We went through those at the very beginning of 4.1. We've got all these divisibility rules, and they're great when they work, but they're not an exhaustive list. It's not all-inclusive. Okay?